Let's continue on problem 25. Now we are going to do 25E. Again, this problem is in page 92 of Segel, and the problem asks, what's the pH of a solution 0.20 molar. We're not too much in the significant figure issue here, so I'm going to take 0.2 molar, and the solution is of potassium acetate. So potassium acetate. So the first thing when we have a problem with a salt is to figure out which part of the salt is going to undergo hydrolysis, right? This comes from a strong base, KOH, so that part is not going to hydrolyze and to cause any change in the pH of the water. But this part here comes from acetic acid. Acetic acid is a weak acid, so this is a strong conjugate base, means that this when put in water, is going to capture protons from the water and it's going to change the pH of the solution. So we have to work on this problem, take into consideration that fact. So first of all, we have to go in the table and get the Ka for acetic acid, which is normally 1.8, 10 to the power of -5. And the first thing we have to do is to write this equation here. The CH3COO minus is going to react with water, right? And it's going to generate an equilibrium. And this is going to give CH3COOH, that's acetic gas, plus hydroxide. If you remember well from class, this is exactly Kb, right? In this direction, from the reverse direction would be Ka, and the forward direction, as written here, is going to be the Kb. So what we have here, we have initially 0.2 molar, right? And a little bit of that is going to react with water and to generate acetic gas. So it's going to be 0.2 minus X, and that would be going to generate here X and X moles of acetic gas and the hydroxide. So the equilibrium constant for this, again, is going to be Kb, or constant of hydrolysis in this case, but then end up being Kb. And the Kb is going to be given by the concentration of acetic acid, CH3COOH, times the concentration of hydroxide, divided by the concentration of CH3COO minus, the conjugate base. As you see here, I don't put water because water is a constant, right? We already know that very well. Now the question is that we have Ka and we have here Kb. So we know also that the Kw equals Ka times Kb, right? So Kw equals Ka times Kb. So if you have then Kw and we have Ka, we can get Kb, and Kb is going to be equal Kw divided by Ka. So let's see here, Kw is, we already know that, it's 10 to the power of -14 at 25 cells. And now we have 1.8, 10 to the power of -5. That's this constant here, right? So then we have the Kb for this reaction. The Kb, let's calculate this thing in here, 10 to the power of -14, 1.8, 10 to the power of -5. Okay, so it gives us 5.88 or 5.9, 10 to the power of -10. That's the KB for acetic gas, okay? The KB. So let's scroll up a little bit here. Have more room for that. And now we have KB. So let's plug in these numbers in this equation, right? From here, we have KB equals, what's the concentration of acetic gas? Is X, right? So X times the concentration of hydroxide, what's going to be X, divided by the concentration of acetic, the acetate, that's going to be 0.2 minus X. And this is going to be equal now at 5.88 10 to the power of negative 10, right? So now you have to calculate here. So one simplification that we can do is that the amount of this reaction is very small. So this X is a very small number. So we can simplify by saying that the 0.22 minus X is nearly 0.22. So that simplification is important so that you don't have a much more complicated equation to solve. Okay, so that's what's going to give us here X squared equals 0.2 times 5.88 10 to the power of negative 10, correct? So this is here, we are going to plug in all these numbers and calculate, and then take the square root of that. Is going to give us X equals 1.08 10 to the power of negative 5. This is X, okay? X, can I go a little bit more here to give you room to see? X is the concentration of hydroxide, right? So from that, we can have the POH is going to be minus log of X, because X is the concentration of the hydroxide, right? So that when we plug in this, would give us POH equals 4.96. But the question asks what's the pH, so you can obviously move a little bit up here so that give a little bit more room for us to write. So now we have pH equal 14 minus 4.96, and the pH of this solution is going to be 9.04. Does it make sense? The numbers and the calculation make sense. That, remember what I said in the beginning, that when you put this base on the salt with this base on water, so the water is going to, the protons of the water is going to be captured because it's a strong conjugate base, right? They are going to remove protons from water. What's going to happen with the pH of the solution? The pH of the solution goes high, right? If you add the protons to water, the pH goes low. If you remove protons from water, the pH goes high, right? So it makes perfect sense now, right? Okay, so that's the solution for the problem.